is given by Bas Spitters on synthetic topology in homotopy type theory for probabilistic programming. It's part of the worldwide plot by homotopy type theorists to take over everything. So go ahead, Bas.
Apparently you're not seeing, let me try this again.
So yeah, you should make sure that you share your desktop and not just that program window, because otherwise the full screen one does not appear.
Yeah, precisely. This is better. This is what I wanted to share.
That's better. Thanks.
Okay, thank you very much for your help. Yeah, as Prakash said, this is a part of a plan of the homotopy type theory community to take over the world. It's mostly, it came from my interest in trying to understand how EasyCrypt works and how we could extend that kind of reasoning. So EasyCrypt is a tool to reason about security properties, about cryptographic primitives, do some game hopping and so on, and how to extend this to continuous probabilities, like probabilities of real numbers. So you've, I think yes. So I think you already, so many of you have seen, well, no, I don't know this very well, or have seen one of the tutorials, but let me just quickly repeat it. So monadic programs, monads are very nice to structure programming with effects, and we can use the Kleistley category, and this is used for example to model partial functions, to model state, non-determinism, and discrete probabilities. Now if we look at how classical probability is modeled, so and I just want to repeat this to give you an idea of there's nothing new here, just to give an idea of what it looks like. So it's measures on a sigma algebra of sets, and sigma algebra is a collection closed under countable unions and joins, and then a measure is a sigma additive map to the real numbers. And then we can do the Giry monad, for instance, on the category of measurable spaces, on various subcategories of topological spaces or domains. Now there's a bit of simplification possible here. So we can look at valuations instead, and these have been very important in domain theory, where you restrict the measures to open sets. If you have a regular measure, then it can be completely recaptured by the corresponding valuation. There are a number of issues, I mean, that we've heard already this week. The category of measurable spaces is not a Cartesian closed category, and it's not a monad on set. So it's so on the one hand, it's not very, the classical approach is not very suitable for programming languages. On the other hand, it also makes reasoning harder. One of the things that's happening in the EasyCrypt system is, for instance, that it's very important that that we start with a monad on sets, and in that way you can only do discrete probabilities. So there are a couple of motivations to actually do this. And what we're doing is using a synthetic approach, and this has been, I mean, this is common in category theory, but specifically I want to
I interrupt for a minute?
Yep.
So on your previous slide, you defined sigma algebra as closed under countable unions and intersections, but not complement. So I'm wondering if that's a typo.
Oh yes,
or is
that's an omission. Thank you. Of course, that should also be the complements. Yes.
Okay, fine. Thanks.
So just to give you the plan of the talk, so I want to develop some richer semantics. So instead of using classical sets, we can use constructive sets, so Topos theory, and this allows us to have some more flexibility. Then I'll say a bit about synthetic topology. So it's doing topology, but using the language of category theory. And then I'll elaborate a bit on this, how once we have the synthetic topology, how we can do probability theory in that setting. That's done using valuations. And then we use homotopy type theory to formalize all of this. The first three bullets actually are completely at the one topos level. But actually to have a to connect it up to say proof assistance and to type theory, it's much nicer to use homotopy type theory. So we go to higher toposes. You're not expected to know too much about homotopy type theory, but I think just by basic osmosis, people have heard the basics about HoTT, and I'll explain more about this. So as so often in this area, we have both a computable, say in terms of realizability, and a topological semantics, say in terms of domains. But I'll give you more in a minute. So the short introduction to synthetic topology. So this goes back at least to Scott's, maybe to Brouwer even in some form or another. So Scott had the idea that wouldn't it be nice if domains are just sets, and this can be done actually by taking not classical sets but using sets in a topos, and this has been worked out very nicely by Martin Heiland and Pino Rossellini. So they really developed synthetic domain theory in that setting. So then you can actually understand domains as sets in a certain topos. And this is done by adding some axioms to the topos. We can actually make a domain-specific language for domains. This idea was also taken up by in synthetic topology, and there's also a long history here. Martin Escardo, Paul Taylor, Steve Vickers, Andre Bauer. More recently, Davorin Lesnick has written a PhD thesis on this topic. So the idea is to have a category where every object comes with an intrinsic topology. So, and all maps will be continuous in this setting. So how do we do this? The basic construct we need here, or the basic observation, is that in classical topology, already the Sierpinski space works as a classifier for open sets, very much in the same way as the subobject classifier in a topos works as a classifier for monomorphisms. So we have in classical topology, we have a correspondence between open sets of space X and maps from X to the Sierpinski space. Now, the observation that was made and the theory that was developed is we can actually forget about a topological space as a set together with a structure of open subsets. Instead, we can use many of these from category theory and from programming languages, and actually just works with the lambda calculus. This is also something that we've seen many times in category theory. We go from a category of nice objects to a nice category of objects which may not be so nice. So this is about a convenient category or a type theory for topological spaces. So that this idea has been developed for domain theory, for topology, for synthetic real computability, and this can again be captured by using such a kind of like a Sierpinski space, a classifier for semi-decidable truth values. And this is a nice way to capture many constructions in computability, realizability. And we can make a common generalization of many of these properties, and this has been done by Pino Rossellini. So one takes a certain subobject of the object of truth values, and then considers all the maps into this. And so these maps are called, well, open or semi-decidable, or whatever the model is you're taking. The dominance axioms precisely says that such monos compose. So what we'll be developing here is we take such a Sierpinski-like space, and then we assume that it has the dominance axioms, and then we're going to develop a lot of theory or some theory about this. This slide is slightly pedantic. So this is for the people that are really into homotopy type theory. What we need, and this can be done in any topos, we need that a free omega CPO completion exists. So this is the omega CPO completion that preserves the order. What we're going to do is we'll be working inside a predicative topos. The details are not too important. What is important here is that this maps very nicely onto the type theory that's present in proof assistance. So this makes verification much somewhat easier. But so if you're working in an actual impredicative topos, then we would certainly have such a free omega CPO completion. If we have countable choice, it would exist. If we have classical logic, it would exist. So now what the gadget we're going to look at is the omega CPO completion of 1. And this will be a dominance. So basically what we're doing is we're adding a bottom element to the 1 point set. And then it will actually look like, you can probably not see my mouse. It will look a bit like the picture of the Sierpinski space that we have here. So we have an open point and a closed point. It's just that the topological spaces that are related to this, they will be more countable. Now there's an extra ingredient we need because we were redoing all of topology. Now we want to say when a space is metrizable, and so a space is metrizable if it's intrinsic topology. That's the one that's given by maps into this Sierpinski space, actually coincides with the metric topology. And then we have the Venn principle. This goes back to Brouwer, but this is has also been studied in a type theoretic or domain theoretic concept, and this is important in computability. So what we'll need later on is that the Cantor space is actually metrizable and compact. And this is something that will actually hold in our models for computability and in our computable semantics. So this will be used to construct the Lebesgue measure. So now we're going to fix a model that comes with such that every object comes with a topology, and I'll give you 2 examples. So one is if you studied the computability theory, that there are basically 2 ways of doing this. So one can take the ordinary Turing machines, but one could also take Turing machines which have an infinite input tape and an infinite output tape. Those are very good if you want to reason about computability on continuous structures, for example, the real numbers or all kinds of other structures. This is called, this was first studied by Kleene and Wesley. They developed what is called K2 realizability, but this is one of the realizability models. And this actually, by a construction by Andy Pitts, this generalizes to a realizability topos. This was also studied by the school of Weyrauch. They come more from a classical background, and they call this the type 2 theory of effectivity. But this is a very standard model for computability, computability with continuous structures. Now what we can do is in this setting, one would have countable choice, and one can take the Sierpinski space to be the set of increasing binary sequences modulo the relation that if such an increasing binary sequence, it jumps from 0 to 1 at some point, we don't care at which point this is. So this is really a countable version of, I see there's something in the chat. Get some input from here. This is really a countable version of the Sierpinski space. Here's another construction. So one model of our axioms is this very natural model in computability theory. Another one is in topological spaces. As we all know, topological spaces behave very badly as a category. And one solution to this is the notion of a topological site. So we make topological spaces into a topos in the following way. So we take the a category of topological spaces closed under open inclusions, and the covering is done by jointly epi open inclusions. And then we take the big topos on this. Well, we could either take a big topos, or we could cut down the category and say we only take separable spaces, for example. And here, our Sierpinski space really is the Yoneda applied to Sierpinski space. So this is again a very nice model where we have a topos where every where clearly every object comes with an inherent topology. This actually forms, and this model has been studied by Mike Foreman. So this is one of the canonical models for intuitionism. So all maps are actually continuous. It's also a very convenient category. So sometimes when people talk about convenient categories for topological spaces, they mean something that's a Cartesian closed category. But this one's much more convenient. It's really a topos. So we have basically all the structure we could wish for. So now we take either of these models. So we take either the computable model or we take the topological model. But since this is a workshop on probability theory, we'd better get into probability theory right now. So we're going to construct the valuation monad in such a setting. So the first thing we need to do is construct real numbers. And in a topos, there are a number of variants of real numbers. And these correspond to either ordinary continuous functions to the real numbers, at least if you're looking at a sheaf topos, or they would correspond to the lower semi-continuous functions. So we can construct we can look at the lower real numbers, and they would be correspond to lower semi-continuous maps into the real numbers. Then an upper real numbers is just the converse. And then we can have the Dedekind reals, which is a lower real number combined with an upper real number and an axiom that they actually touch together, as you would expect. Now, evaluation is a map, and this is important. So the standards, if you look at evaluation on a topological space, it will in general not be a continuous map from the open sets to the real numbers, but it will be lower semi-continuous. So that's why we need a map from the open sets to the lower semi-continuous real numbers. Moreover, it should satisfy a number of axioms, and those are just the ones you would expect. So it's monotone, it has the satisfies the modular law, it is omega continuous, so it maps increasing sequences to increasing sequences, and at 0 it's 0. And then we could consider an integral. And the nice thing about integrals is they are actually continuous. So if we look at the map, any map from a space A to the say the positive Dedekind real numbers, we would actually get a continuous map from that space to the Dedekind real numbers. And it satisfies a number of properties. So additivity, monotonicity, and omega continuity. And then what one can prove completely constructively is that we have a homeomorphism between integrals and valuations. And this is just the Riesz theorem. What is important, because we're in a topos and we're not in the topos of classical sets, we need a constructive proof. This is something we've done with Thierry Coq already a long time ago. And this can be done when A is a compact regular locale. So we need some conditions on A, and that's also important in topology, that we need A to be, say, compact Hausdorff. So a compact regular locale is the localic variant of a compact Hausdorff space. There was a generalization of this by Steve Vickers, who showed that if instead of taking compact Hausdorff spaces, one takes any topological space, or in fact any locale, one needs to replace the integrals by lower integrals. But then still one gets the correspondence between valuations and lower integrals. And what we developed here is to do the whole story again, but synthetically. So in synthetic topology, just from basic axioms about this Sierpinski object. Now there's a question, and so this is for the experts on homotopy type theory. One can do this. This was already mentioned in the hot book that this could potentially be done. It wasn't done there because there were already many experimental theories. But here we actually carry this out. So what we learned is that the lower reals are actually the omega CPO completion of the rationals. That's what one hopes. We can avoid countable choice. So there are many toposes in which we don't have countable choice by indexing with this Sierpinski object. So that's also, I think, a nice observation. Quotient inductive type. Sorry, that's a question in the chat. A quotient inductive type is an experimental feature in homotopy type theory. It allows one to, at the same time, develop a set inductively, a relation over it inductively, and then quotient by that relation, all at the same time. This is important, for example, in the hot book to construct the real numbers. And it was also important in the omega CPO completion. Another thing that was observed is that much of this synthetic reasoning is actually very close to geometric reasoning, and here I mean geometric in the sense of geometric logic. So the logic or the mathematics that preserved under pullbacks of geometric morphisms between toposes. So what we need to avoid here is the power set, and we need to avoid countable choice. So there's a very nice parallel here, and it may not be a surprise because we're really reasoning synthetically about open spaces, and that's also what geometric reasoning does. So it's it makes sense, but still I think it was nice that it actually works out. We also proved the Fubini theorem, which of course is I see there's another answer in the chat. So the Fubini theorem mostly works again in this setting. It works for locales. I expect it to work for a nice subcategory, and I think that this also came up in one of the other talks, that we don't always have full Fubini, even in for ordinary measure spaces. Of course, Fubini comes with conditions, so that it may not be too surprising. And we have Fubini for all locales if we look at the Giry monad on locales, but in this case we need some conditions. It is possible that we restrict to a certain subset of this topos, which still has enough structure that we could actually recapture that. And then, as I said, so we build all this theory completely synthetically, but now, of course, to get off the ground, we really want to see that we can build certain concrete measures. And in this case, what we showed is that we can do the Lebesgue valuation. But of course, there are many similar valuations that one can also do in this way. Now, let's connect this to probabilistic programming. So in general, the Giry monad, but this is something we've seen a number of times before. We have a functor from between spaces. We have a unit operation, which is the Dirac measure. And then we have a bind operation, which is basically integration. And then the bind operation can be written in Haskell style in this way. What is missing, and that's what I said before, measure spaces don't form a Cartesian closed category. So to interpret the full lambda calculus, we need what is called T exponents. So we have maps from we need that the Kleisli maps are actually objects in our category. So this is not supported by the standard Giry monad, but our topos or our homotopy sets, if we're in homotopy type theory, we can actually obtain such a higher order language. So we can, because we're using sub-probability valuations, and this is also something that other people have observed, we can actually get something that's omega CPO enriched. So this means we can interpret PCF with a fixed point operator in this setting. So we have a very rich semantics. We even have dependent types in this setting for a probabilistic programming language. Now we had, so most of the story that I told you before, we had done, and then I met Daniel Wang, who was writing a PhD thesis with Greg Morset, and what he had developed was a programming language called Augur. This was version 2, where he was very much involved in writing a compiler to graphics cards for this this Augur language, and he showed that this compiler actually preserved the good semantics of this programming language. So he came up with the semantics in what are called topological domains. So these are domains with an extra computability structure. And then one came to visit, and we worked out together that actually if you unfold the Topos theoretic development that we did using this K2 realizability, so that's the standard realizability Topos for computability, you get precisely the same interpretation as they've done in topological domains. So this is another strong argument that this is a very natural construction. So this is always very nice if two people come up with a very similar idea. And the nice thing about Topos theory, of course, is that you can precisely do this unfolding. Finally, let me say a little bit about HoTT. I mean, it's part of the big scheme of taking over the world, but actually, my motivation for this was more modest or more natural. I had been working with the EasyGrid prover system, and that only does discrete probabilities. But we were also interested in things like differential privacy or machine learning, and there you actually need continuous probabilities, and that's much harder to do in prover systems because your operations, the operations are no longer types. So what we did here was to actually work directly on types, and then you can use all the language of type theory in a very natural way. The type theory also gives you a programming. Type theory obviously gives you a programming language, but in this case, it also gives you a programming language with a very expressive type theory. One thing we need to do in a natural way is we've added a few axioms to type theory, the ones that either hold in topological spaces or on its topological topos or in K2. We need to give a computational interpretation to that, but that's something that has been done before, and we can really see the contours of how to do this very nicely. There's some details to be filled in, but for example, for the fan functional, this has been studied quite well in synthetic topology and the computational interpretation of that. So the ALEA library, so that's I alluded to this a number of times before. The ALEA library, it's the basis for the CertiCrypt and later the EasyCrypt system. So this is a standard system for reasoning about probabilistic programs. So there what they use is a discrete measure in Coq, but again, so this only works on discrete spaces. So we need to have measures on sets, not general measure spaces. And then the presentation of the Giry monad goes via a CPS translation, continuation passing style translation. And what I really tried to do was to follow this kind of development as much as possible. And I think we've achieved that. So that's one reason of using homotopy type theory. If you're working in this library, you want to write down a coin flip, here's what it looks like. But I think most people would be able to write down such a thing in a functional style. So why do homotopy type theory? Well, Coq and most type theory based proof systems, they lack quotient types and functional extensionality. There's what a usual solution to this is to use the exact completion of type theory, which is called setoids in a type theoretic content setting. The nice thing about univalent homotopy type theory is precisely it's the internal type theory for such generalizations of setoids, groupoids, and so on. And we use the HoTT library to actually formalize this whole construction in a proof system. Now, what I've been telling you is how to do toposes, but now I'm suddenly switching to type theory. So how do we do this? Well, if you cut down homotopy type theory to the set level, so this is the level where the identity types are actually quite trivial, then we precisely get predictive topos. The only thing is we have it actually has large power objects, but those are large. Now it has been proved that homotopy type theory can actually be interpreted in higher toposes. So these are in particular toposes where you also have universes. So here what we could do to interpret the whole thing, including the universes and all the higher structure, is to take the higher topos over a topological size. And then the H sets would actually correspond to this. We can also do constructive models because the cubical stacks that are developed by Giry, they actually form a constructive model of homotopy type theory that combines sheaf or stack models with this. And so we can also extend our topos model actually to type theory. And then there's some development on lifting the realizability topos to a model of homotopy type theory, but that's not done at the moment. But there's a lot of interesting results in this direction. Now to tell you a little bit about the implementation. So what we've done is we've built on what is called the math classes library and an experimental induction recursion branch. So this is a feature that's not standard in the Coq proof assistant, but it is available in Agda, for example, and it's currently being added also to Coq. So we need quite a few new features, but also what I'd like to emphasize is that this kind of topos theoretic or categorical reasoning actually has a lot of influence on the design of proof systems. So that's also why I think it's important for this audience. By using category theory, you can actually improve these proof systems. Now some related work. You've seen Sam Staten talk before. So I'd like to compare with the work they've been doing on probabilistic programming languages, which has some of the same ingredients. So what we did here is we started from the observation that the category of topological spaces is not Cartesian closed. So what we first do is we define a convenient supercategory. For example, quasi-topological spaces, which would be concrete sheaves over compact Hausdorff spaces, and this would be a quasi-topos. But this is very similar to the big topos. So the big topos is, again, it's a convenient supercategory of topological spaces. And then once we've done step one, we actually add probabilities to this setting. What this other group has done is using some of the same ingredients, but they reverse the order of these constructions. So first thing is they start with the standard Giry model of probabilistic computation, and then use this category or this site, and then obtain the higher order structure by using a tailored form of Unada. And it'd be really interesting to see what is the connection between these two constructions, but I haven't been able to work that out precisely. But it feels like it has similar ideas. to the construction we've been pursuing. So just to sum up what I've been trying to explain to you, so we can do probabilistic computation very nicely in a setting with continuous data types. We have a formalization of this in homotopy type theory, because this is a very natural machine-supported environment for doing Topos theoretic reasoning. We have an experiment with synthetic topology inside homotopy type theory. This hasn't been done so much before. And then we have an extension of the Giry monad from locales to synthetic topology. So the Giry monad was already done on locales, but now we can actually lift it to a bigger setting where many of these constructors are sort of more natural. And then what I was very excited about is this model of higher order probabilistic computation that's present in this Augur system actually uses precisely the same semantics. So this, I think that this is an exciting direction. So this is what I wanted to tell you. Thank you for your attention. I'll take questions now.
Thanks very much, Bas. So if anybody has questions, please unmute yourself and ask. But let me start with a question that was asked on the chat by Robert Ferber. So he asks, isn't it the case that the constructive Riesz representation theorem is for continuous valuations, not merely omega continuous ones?
So here, so that's I believe that's right. So the interesting thing is here, everything is done synthetically, so we can actually be fairly flexible. So we can be parametric in the in our Sierpinski space, so that the reasoning works for both.
I see. Okay, Alex Simpson has a question.
Yes, hi Bas. That was a very nice. Hi, that was a very nice talk. So can you clarify a little bit at the start? You said you wanted your probability monad to act on sets, but then it seems you're getting it to act on locales. So is there a tension there, or what's the resolution of that?
Well, the resolution of that is that we actually lift locales or topological spaces to a topos, so then they become constructive sets.
So internally it's acting on sets.
Internally it's acting on sets, yeah, precisely. And every set comes with a topology given by the maps into the.
Okay, right. So, yeah, thanks.
I see Sam has a question.
Yes, Sam, go ahead.
Oh, thanks. Yeah, no, thanks for your talk. Hi, do you know how much other things from probability measure theory go through in the toposes you talked about, like Radon-Nikodym, Kolmogorov extension, and stuff like that?
Radon-Nikodym is slightly complicated already in the constructive setting. It needs some. I mean, the observation is that differentiation is generally not a continuous operation as opposed to integration. So you'll need some side conditions on the one to be differentiable or absolutely continuous with respect to the other. And I haven't looked deeply into this, but it's yeah. So that would be the general gist of an answer, I think. So you need some side conditions on differentiability of one measure with respect to the other.
All right, thanks.
Okay, Dario, go ahead, ask your question.
Yeah, I'm not an expert with synthetic topology, so I was just wondering what the status of Borel measurable maps are that aren't necessarily continuous. So say equality tests between real numbers. Is that just ruled out, or is there a way of getting those into the model?
Those are not naturally there. Let's see, how would you put them in? So this would have measure 0, of course, in the real numbers. If you look at the diagonal.
Yes.
Yeah, I don't directly see a way of talking. I mean, representing equality here, because it's not a continuous operation.
So
I mean, generally that's an issue in constructive mathematics or computational mathematics. You won't have an equality test on the real numbers, but you would have an approximate equality test, and I expect something similar to hold here.
would it be possible to build a topos on top of measurability as a fundamental notion instead?
I think that's what the group around Sam Staten has done. So they start with a set of measurable functions.
Sam, what do you think? I always felt like this has a different upshot. Or maybe Sam isn't.
Yeah, no, I agree with Bas. That's sort of what we did. Yeah, I agree. Yeah, thanks.
Okay, thanks.
There's a question from Tobias.
Yeah, right. So thanks for the talk. Do you see any role in any use for the higher homotopical structure, or maybe at the other extreme, do your valuations always factor through the H-set truncation?
So, I mean, most of what I presented in the beginning was on the one Topos level, and so the connection with HoTT is so what is important is we need some kind of extensional type theory with good computational properties. So we did it in a setting that we have for that, and that's homotopy type theory. What we also do by using this using homotopy type theory is that we actually have a good treatment of universes, which I think it would also be interesting for computation and formalization. I can even, so even now we're reasoning with EasyCrypt, for example, you can feel places where it would be natural to have a universe, to use a more type theoretic way instead of the higher order logic. So I could certainly see that having a universe could be convenient. I haven't thought about how these constructions would generalize to groupoids or anything like that.
But don't they natively apply to any? I mean, then any type.
They apply, but as you so everything factors via sets. So it's
okay. Yeah. Okay. Thanks.
Yeah.
I have a question, maybe.
Yeah.
Or it's actually two questions. So one question is, how is this related to Markov categories? Like, is your Topos a Markov category, or is there any differences? And follow up to the equality check, is there something like a semi-decidable inequality for real numbers? Because
so the second one is that's a good point. Yes, indeed. There's the inequality would be a map to the Sierpinski space, at least for most good spaces, I guess. At least for the real numbers, for example, that would be the case. About the Markov categories, that's a good question. I haven't thought about that yet, but that's an interesting question. Yeah, sorry, I
Okay,
don't have more to say. I haven't thought about it.
Well, if there are no more questions, let's thank Bas for another great talk. Thanks very much, Bas.
Thank you for the invitation.
Yeah, and there I figured out how to do clap on Zoom. Okay, thanks everybody for attending this session. Very interesting talks, both of them. And I look forward to seeing you guys at the rest of the sessions.
I'll be available
Okay.
on Zulip for questions.
Great, great. Thanks, Bas.